I looked for this in the reference sheet. I could not find anything about it. Is there a way to route the internal voltage reference to a pin?
Oh, good question. Is there a way of it routing the internal reference voltage to a pin? There's actually two references internally. One is called Vref, and the other is Vref. There is no way to route, that I know of routing Vref to a pin, but you can route Vref to a pin. So you could use Vref. How else, but so the question is, if you can't actually route Vref to a pin, how can you measure the voltage of it? So that's really the summary of one of the questions on the homework. Which one was it?
Last one.
The last one, which would be, yeah, okay. So there's a couple of ways of doing that, but I'm not going to mention them right now. But after all, the internal reference is connected to one lead of a comparator. Okay. What about any other questions on lab 1, on homework 1?
For the Thevenin equivalent.
Yes, for the Thevenin equivalent.
For alpha high, there are 4 pairs.
Yes.
And to plot, you want an IV curve for the 4 different alpha high.
Yes, IV curve.
Okay.
Uh-huh.
And is that the only?
So, let's think about Thevenin equivalence. We have a Thevenin equivalent voltage source, which has a value of, for logic high, has a value of what?
4 options.
What?
There's 4 different ones on the data sheet.
No, there's not 4 different voltages. There can only be one Thevenin equivalent voltage. There's 4 different measured voltages. So you have a Thevenin equivalent VT. You have some RT. You have some external load. Now this is outside the circuit. And what you're measuring, what's in that chart is V measured. Right? That's what they're measuring at some current flow. What's VT? Oh, come on, guys. It's a CMOS pair running between VDD and ground. What's VT?
Is it VDD?
It is VDD. Because if you don't put any load on a transistor, the output value is going to float up to the supply. Right? This is just a CMOS inverter output, so it's going to float up to the supply. So VT is VDD. What I'm asking for is this resistance, not this resistance. Does this kind of scrape 2 neurons together back from circuit theory someplace? Or is it physics? Where'd you learn this? 2100? Physics 1? I don't know. I don't remember where I learned it either. Any more questions on homework? Yes?
How do you choose the prescaler?
Oh, well, yes, prescaler for the timer. So what you're trying to do is you're trying to measure the time constant of some circuit that's charging up after a square wave is applied to this circuit. And what you want is the charging time with a minimum, but you're making the measurement digitally with a counter. And if you have less than 100 counts, then you can't possibly do better than 1% accuracy. So, and you want the number of counts to not be part of your error budget, so you have to have at least 100 counts. And you can't have greater than 60,000 counts because the system overflow, the 16-bit counter overflows to 65,000. You can't have more than 2 to the 16th minus 1 counts. So you have to arrange the time constant so that you fall between 100 and 60,000 counts of the timer. You have lots of degrees of freedom. There is no unique solution. You can vary R. You can vary the prescalar. You can vary the clock. Oh dear, vary the clock. Let's talk about clocks just a little bit. Down on the ProtoThreads page, which, among other things, you should read, there is a set of a header that you can download, or if you download any of my zip files, you'll get one of the headers. But there's a file which sets all of the clock rates, config.h. If we look at config.h, there's some header in there which attempts to suppress some plib warnings and do some other stuff, links plib and standard I/O. But the main thing that config does is to set up the timing. And so pragma is a phrase in C that says, this isn't standard C, folks. If you are a C compiler, don't even look at it. But the microchip environment notices the pragma and sets some internal switches in the CPU to choose a clock rate. So this says to use the internal clock with the phase lock loop option. The internal clock runs at 8 megahertz plus or minus 0.9%. The phase lock loop is a device that has a frequency divider on the input, a frequency multiplier, and another divider on the output. Yikes. That's horrible. It turns out that the input of the phase lock loop has to be 4 megahertz plus or minus 20%. So since the 8 megahertz is what we have coming in from the internal oscillator, we need to do a divide by 2 to get it to 4 megahertz. And this is the FPLL input divisor divide by 2. So what's coming out of here now is 4. I want to set the frequency to 40. Turns out there doesn't happen to be a multiply by 10. So I did a multiply by 20. FPLL mult set to 20. And then that's now at 80 megahertz, 20 times 4. So now I do a FPLL output divisor by 2 to get it back to 40 megahertz. So the CPU frequency of this config file is 40 megahertz. You could change that. You can change it to anything you want up to 80 megahertz, except the CPU won't run at 80 megahertz. It may well run at 60 or even 64. It probably will not run at 70. It's rated at 50. The closest you can get with the PL loop is 48. Now, separately, you could take this frequency and do another divide to get the I/O bus frequency. I/O bus frequency. The I/O bus frequency then, the peripheral bus divider, I'm setting to 1. So the peripheral bus is running at 40 megahertz as well as the CPU clock is running at 40 megahertz. Then these last two lines turn off a bunch of options so that you have all of the I/O pins available. Otherwise, they're taken over for some other special functions like debug and hardware external clock. So what these lines do is to set the CPU frequency to 40, the peripheral bus to 40, and then down lower in the code, I, by hand, define the system clock to be 40 megahertz and the peripheral PB clock to be sys clock. And that's because at the time I wrote this, I couldn't figure out how to read the internal registers to get out the stuff I had just set. There's two other commands in here. One is that you can use Vref, that's CVref. You can use Vref as an I/O pin, a debugger I/O pin for the tasker, but for the threading package, and it'll put out a voltage proportional to which thread you're executing. Don't do that right now. Comment out that define. Comment it out. You always, without fail, need to read config.h in a project and make sure that what you have in config.h is what you need. If you fail to comment out vref debug, the DAC won't work. So you have to comment this out. You're also going to comment out the baud rate and use UART serial. So you're going to comment out all of these. You must read and modify this file. You have no choice.
What won't work if you comment out the last two lines?
These guys?
Yeah.
The UART takes over pins 21 and 22. So they become unusable for general I/O. And they're dedicated. If you do not comment this out, then pins 21 and 22 are dedicated to serial communication. So, now let's pop the stack back up to the question you asked. I forgot to push it, but there was an implicit push. And note that the peripheral bus clock is 40 megahertz, unless you change it. So, going back to problem 3, then you have only, instead of having 3 variables, now you have only 2. You have a resistance value that you can change, and you have a timer prescaler that you can change. There is no unique solution. They have to be compatible. If you set the prescaler to 1, that is going to define a resistance. If you set the prescaler to 2, it will define a resistance twice as big. You get to choose those. Now there's some reasonable limitations. For instance, I believe it says in the, it says right here. Yes, it says right here that it has to be greater than 10 kiloohms for the accuracy, for the constraint of the discharge accuracy. So it's got to be greater than 10 kiloohms. There's another implicit constraint which you may not know, and that is that we don't have any resistors in the lab greater than 10 megohms. So if you come out with a value bigger than 10 megohms, it means you've messed up the units. You scaled something wrong. So our group today had a value of 10 to the 11th ohms. My fingerprint on a piece of glass is about 10 to the 9th ohms. So you can guess that 10 to the 11th ohms is hard to come by. It can be done. Can be done if you wash the board, if you guard the board and wash it with isopropanol. But that's an unreasonably big value. I would guess that the one problem with very high values of resistance is you start getting noise because you're picking up EMI, electromagnetic interference, from other parts of the circuit. The higher the resistance, the more EMI. So you have a lower bound, which is defined by the accuracy of the discharge, and you have an upper bound defined by EMI to be 1 or 2 or 5 megohms or so. Any other questions on the homework? Now, that should be the end of that question. Did I actually answer something useful?
Yes.
Okay.
For the number 4, for the maximum current you can source from the sum of all pins, is that just a matter of adding all the pin?
No, it is not a matter of adding all the pins. It's a matter of looking at the data sheet to find the entry for the maximum dissipation of the package. There is a section always in every integrated circuit data sheet. There's a section that says absolute maximums. Those are the values which, if you exceed, you can guarantee you will destroy the chip. They're not the safe levels. They're the levels at which you are guaranteed to destroy the chip. That will tell you how much current you can draw from the chip. And that is less than the sum of driving all of the I/O pins to their maximum. Anything else?
On question 6, it talks about step 2, and then it talks about discharging the capacitor. Step 2 on the lab refers to charging the capacitor.
Oh, good. I have a typo. That's yeah, classic, isn't it? So I think you could probably infer that the words about the charge discharge are more likely to be correct than the number of the step. If you put something on Piazza, I'll fix it. Anything else? So, let's go back to the lab. So this is, yes?
Is there a format for homework that should be sent in? I know Piazza said email to the TA, but does it matter? Like handwritten scans or typed up?
As long as the TA can deduce what you mean, I don't care. So it doesn't have to be LaTeX. It doesn't have to be gorgeous. It can be a photograph of your handwriting, as long as it's modestly legible. I'm fine with that. So most people, I think, are going to build the big board, but if you decide to go with just the microchip, the microstick, then what you are going to end up doing is mapping these pins to the TFT and DAC by connections across whiteboard. So the TFT page has some wiring images of that, but I'm not going to talk about that right at the moment. Here's a list of all the connections that you need to make. If you're building the big board, these are all made for you. So all you have to do is connect 3 wires, really, to the CPU. We talked last time about peripheral pin select and the mapping of of logical signal names through PPS, peripheral pin select, to logical pin names, and then from logical pin names to actual pin numbers. Are there any questions on that? That is just a horrible mess. It's meant for maximum flexibility because the internal signal can be mapped to any one of 8 up to 8 logical signals, which are then mapped to different pins on different packages. So the reason they do this is that a 44-pin package is going to have a different set of I/O capabilities than a 28-pin package. So this is why there's this two-step indirection, which means you always keep 3 documents open and scan back and forth between them. Any questions on that? Well, I'll show you some examples. Software, blah, blah, blah. So let's go down and look at some actual code. Oh, before we look at code, though, we have to talk about more about ProtoThreads. The environment you're going to be using to code is a very lightweight threader. So you're going to have several threads of control, or think of it differently, you're going to have several C functions, each one of which has an endless loop in it, a loop from which you never escape. And you're going to treat each one of them as an independent execution environment. This happens to be, the library is written as C macros. It is not preemptive. It is a shared environment. So that means that each thread can hog the CPU unless you're careful with your coding. It also means that there is one stack. It's not stackless, it's one stack. And that means that functions can step on each other's environment with ease. So you have to be careful. This would never fly in a multi-user environment, of course. There's no protection on anything. But since it's a single-user small system, you have complete control over the code that runs. You can make sure that the code plays nicely, that each thread plays nicely with every other thread. There's support for a thread to wait for an event, a semaphore, or a timer event. You can spawn a thread from a thread. And having no preemption is a mixed bag. It means that you never get a context switch in the middle of an arithmetic operation because you choose when the context switch is going to occur. It also means, however, that you cannot guarantee real-time deadlines by using threads. Because you can't force, the scheduler cannot force a thread to stop. If you absolutely have to guarantee a real-time deadline, you use an interrupt. This will happen in Lab 2, where you're going to need to do audio synthesis at 44 kilohertz, which is faster than the threader can actually change contexts. And in Lab 4, when the motor controller is going to have to run at a very, very regular 1 kilohertz control loop rate. And the control loop will have to be in an interrupt service routine to get the very regular 1 millisecond rate. You get to write the scheduler. But that's quite easy. So there's several versions. The most complete version is version 1.2.1. Most of my examples are updated, except the very early ones from early last year are still at 1.1. But you can change that by using a different include file. There's a set of functions. You can initialize a proto-thread. You can wait on a thread. You can wait. You can wait until a condition, wait while a condition. The conditions can be quite general logical conditions. You can spawn, you can yield. Yielding says, I'm not going to wait for anything in particular to happen, but I'm going to give the scheduler a chance to let somebody else execute. So this is a polite thing for a thread to do. It's not required, but it's polite. If you do a yield until, that is also a yield, but it depends upon a condition. I added a couple of more functions. I added a function for yielding for a certain number of milliseconds, the ability to return the number of milliseconds, and then some rate loop scheduling that you probably won't use. So, as an example of this, let's go back and look at a program in Lab 1 that exercises a couple of things you're going to need to do. It's going to, oh yes, great. It's a timer cat pure. That's supposed to be capture, but it's pure cat. And so what this does is to generate two precision square waves on two output pins. Precision in the sense that I know exactly how many cycles each one is going to take. So I'm going to set this up so I get a 50% duty cycle square wave at precisely 10,000 cycles and a 1/4 duty cycle wave at the same frequency at 10,000 machine cycles. I'll put those on pins 14 and 18. Take the output, those two outputs, feed them back into the input capture, which is what you're going to have to use to measure the capacitance rise time. But I'm using it to measure the output of a square wave generated by the system itself. And then we're going to display the capture time on the TFT LCD. So we're going to start by including config.h, which you must edit without fail. You can cut and paste nothing. You include PT Cornell. Oh, look at that, 1.1. You need to change that to 2.1. You're going to need the TFT master and graphics, which will all be in the zip file if you download the zip file from the lab. And we're going to need standard lib. We're going to need a couple of, we're going to define two thread structures. The thread type is PT, and we're going to have one that prints an input, prints an interval, and the other one prints the absolute time, or actually keeps the absolute number of seconds since boot time. There's going to be a global variable which is systime in seconds, And we're going to define shorts, not ints, shorts. Those are 16-bit. Shorts are 16-bit. Capture 1, last capture, capture period. The reason I'm doing that is using shorts is that the timers are 16 bits. When the timer rolls over, if you set up a timer to roll over after it maxes out, then it will roll from FFFF to 0. And if you compute capture versus last capture, that subtraction is correct through a rollover. Think about it. Only if you're using shorts. If you're using ints, it is not correct. But if you're using shorts, then you don't have to have a special case for when you happen to be timing an interval across the timer rollover. So, first thing we're going to write is a capture interrupt service routine, and this we'll set this up down lower in the code, but this capture service routine is going to be triggered. It's the event that triggers it is going to be that whatever the source of the capture is, in our case, it is going to be the comparator changing state from 0 to 1, logically from 0 to 1. The value of a timer is copied into a register. 70 cycles or so later, the interrupt service routine actually executes this code, which reads the capture register into the variable of your choice. If you merely read the timer in the interrupt service routine, you can be 70 or 100 cycles off. That's a lot if you're running at full speed. Because you're capturing the timer in hardware before the interrupt service routine actually occurs, you get cycle accuracy. It is the only way of getting cycle accurate time captures. We get slowly into the interrupt service routine because it's got to save the state of the machine. We read the capture. We subtract this capture from the last capture. Subtract this capture from the last capture. We update the last capture. We clear the interrupt flag because in this architecture it's not automatically cleared. And what happens if you don't clear that flag? What would you guess happens?
I guess it would never fire again.
That's one reasonable guess. In fact, it fires all the time. Those are the two possibilities, right? And in this case, it fires on the next available machine cycle forever. And you say, huh, that's funny. My TFT went dead. Must be a bad TFT. So always clear the flag. So this interrupt service routine is going to happen asynchronously with respect to any of your scheduled threads because it's going to depend upon a hardware event, which is this waveform crossing some threshold. Now, in the print thread, so this is a static P thread, and the syntax is as given here. We signal the beginning of the thread. We have some buffers, but notice that any variable that you expect to be valid between entrances into a thread have to be declared static. It's because there is no true stack here, and these functions are actually running as coroutines. Here's a piece of cryptic stuff. How many people know what Duff's device is? Does anybody know what Duff's device? You do?
Yes.
What is Duff's device?
Duff's device is a technique for loop unrolling, which makes use of the very peculiar fact that in C, a switch statement can put cases inside of loop construct inside the switch. So you can open a switch, open a while loop inside the switch, and make your cases go into the middle of the while loop.
Beautiful, thank you. It is, that's better, I could have done, thank you. So that's exactly right. It is legal in C to jump into a while loop using a computed goto. Oh, have you ever even heard of a computed goto? It takes a value and jumps to an absolute label in the program. It is so unstructured, they don't even tell you about it in programming class. This is evil. It's all hidden from you. You can't see it here. It's happening. And all of these are running as coroutines in a big switch statement, in fact. But you can't see that. All you see is PT begin. So what we're going to do here is we're going to do a set cursor to 00 is 320 by 240 display. We're going to set a text color. We're going to write a string, which reminds us how to hook the darn thing up when we're using it. Then we're going to yield for 200 milliseconds. So this is updating about 5 times a second. That's reasonable for human interaction. You might go to 10 times a second, but not any faster than that. Then we're going to do a fill round rect, which is the easiest way I've found to erase text. So we're going to just do a fill rect, boink, 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 with black. That erases the last text I drew. The syntax is x, y, width, height, and radius of curvature of the corners of the rounded rectangle. Then we're going to set the cursor to 050 and generate a string using sprintf to convert numbers into a string, and then write the string to the TFT. And then we are going to, and we're embedding this all in a while one, because you may not exit a thread. You must not exit a thread. There's an end thread. So how does the system get control again? How does the scheduler get control? During that yield.
So I noticed that at the very bottom you're manually scheduling these threads yourself. So how does that interact with yielding for a specific period of time?
So we'll see in main that I'm scheduling these threads as fast as I can schedule them. There's no delay in the scheduler. It just is going through over and over again. If a thread is yielding on a wait, when it gets scheduled, that wait is checked. If the wait is not yet valid, it bails out again and goes to the next thread.
So it tries to schedule, but doesn't really get scheduled until that wait is over.
That's correct. So there's another thread which is measuring time, and all that is doing is waiting 1,000 milliseconds and incrementing the second timer. So systime in seconds is keeping a 1 second tick, a very approximate 1 second tick since boot time. It's probably only good to 0.1% or so, or probably less than that, probably less than 1%. Main is where all of the ugly stuff occurs. Yes?
I'm not really understanding why it exits during the yield. Could you go over that again?
So the function doesn't exit, it pauses, and something else gets to execute.
But what makes the other thing execute?
The scheduler. So the scheduler is saying, try thread 1, try thread 2, try thread 1, try thread 2. If thread 1 is ready to run, it runs. If it's not, it goes to thread 2 and tries that. If that's not ready to run, it goes back and tries thread 1.
Is the
approximate 1 second that we get from using threads okay for lab 1, or do you want us to use interrupts to measure system time?
This is good enough. So what we need to do, we need to set up 2 timers. We're going to set up a timer. We're going to set up timer 2 to run the output compare units. So to generate the square wave. And we're going to set up timer 3 to be read by the input capture. Cat pure. The input cat pure. The input capture. So we need to set up timer 2. We need to set up 2 output compares because I'm generating 2 square waves. We need to set up timer 3, and we need to set up the input capture. You're not going to set up output square waves. I'm just using this as an example. You are going to set up the input capture. And so here we get into the gory details of PLive. We're going to open timer 2. We're going to turn it on, of course. We're going to set the source to internal. Internal means coming from inside the chip and not from an external pin. We're going to set the prescalar to 1. And we're going to set the timeout to generate period, which further up in the program I set to 10,000 cycles. 10,000 ticks of the clock. And I initially configured an interrupt for timer 2 before I realized I don't need an interrupt to generate square waves. This is hardware, folks. There's no interrupt running on timer 2. Rather, timer 2 is directly telling the output compare hardware to generate the square waves with no software. So I commented it out, and I also commented out the flag. So I left it there as a reminder to you not to use an interrupt. Now, if you go through this and say, he must have been full of it, I'm going to uncomment those. What will happen? What will happen? This causes a really obscure error. And that is because you have initialized an interrupt for which there is no interrupt service routine written. And the behavior of that is undefined. Now, what this compiler does, say, Bozo doesn't know what he's talking about, let's do a system reset. So the default behavior is you turn on an interrupt for which there is no interrupt service routine, and the behavior will be reset as fast as possible, forever. So when you say, that's weird, the TFT keeps clearing over and over again, you say, the next thing you think is, what interrupt did I turn on by accident? Don't uncomment that. Then we're going to open OC3. Why OC3? I don't know. Output compare 3. Turn it on. We're going to associate it with timer 2 as a source and make it a continuous pulse with the generate period, 2 parameters, generate period and the generate period shifted by 1. It turns out that means clear at the generate period and set again at half the generate period. So that's a 50% duty cycle square wave. Furthermore, we have to set PPS output. We have to associate the OC3 signal, the PPS output OC3 signal, with a logical RPB9, which then we have to look up on the data sheet and say is pin 18. And we just have to know it's group 4, but of course you can get that off of the nicely annotated PPS diagrams I gave you. Again, I thought initially I had to set a port pin as an output to do this, but no, you don't. That's why it's commented out. It's because PPS overrides the I/O setting of the pin. The PPS system overrides the default digital I/O setting. OC2 then is turned on the same way with a slightly different generate period, and using PPS output from group 2, OC2 is set through RPB5 to pin 14. Then we're going to configure timer 3 to be free running. What does it mean, free running? It means that the reset value is set to full scale. So the reset value at which the timer automatically resets to 0 is set to FFFF. 0 is the next logical count on a wraparound. So this is so-called free running. There is no particular timeout on this. Again, running at full speed with an internal source. Then we open a capture module that's going to grab timer 3 on every rising edge, capture using timer 3 source. We're going to configure an interrupt for capture because this we want an interrupt for. After the capture occurs in hardware without your interaction, we want to be able to know that that capture actually happened 80 cycles ago and grab the value and put it into a variable. So that's what's happening. So that the config interrupt here then turns on the capture, clears its flag, and connects the input capture with RPB13 through group 3 of the PPS inputs. Then all we have left to do is to do the TFT dirty work, initiate the hardware, begin it, fill the screen with black to erase, set some rotation, cursor, play with these parameters. Nice thing about graphics is you can figure out what it does by changing the values. There's a PT setup. We have to turn on interrupts. Oh, if you leave that line out, interrupts never occur. The scheduler fails. Nothing happens. Initialize the threads and now schedule the threads by doing a PT schedule, just round robin as fast as possible. Is thread 1 ready? Nope. Is thread 2 ready? Is thread 1 ready? Is thread 2 ready? And they'll execute if they're ready, otherwise they return.
Is there a reason you didn't use timer 1 at all? Or was that just
Is there a reason I didn't use timer 1? No, there is no reason. In retrospect, I should have. Because there are 5 timers, 1, 2, 3, 4, 5. 1 is actually a simpler timer than the other 4. And I should have used that, and I probably will port the code to that sometime fairly soon. 4 and 5 can be grouped together to make a 32-bit timer. 2 and 3 can be grouped together to make a 32-bit timer. Furthermore, 2 and 3 have lots of special functions. For instance, timer 3 can trigger the A to D converter. Timer 2, I don't remember, there's a couple of special functions on each one of them. Timer 4 and 5 are more generic. I should have not used timer 5. That's what you're kind of inferring from my choice, right? Yeah.
When you turned on that interrupt, how did the compiler know to associate that with the interrupt service routine you wrote earlier? Because you didn't actually use a function pointer to that routine, which I'd sort of expect you to do.
If you look back in this header, there's a vector description which says that this interrupt is associated with the input capture 1 vector, which is a memory location that then indirectly points to the code. So the compiler builds a table, a vector table of entry points of the interrupt service routines. That vector table by default is pointed to reset. That's how it does the reset default. Did I answer what you?
Yeah.
Okay. What else? So this is kind of the basic code. There's lots of variants on this. What you're going to want to do to start is to download this zip and build it. It should build. It should download. You should be able to put it on the chip, and unless you hook pins up, either 14 or 18 to 24, it'll do nothing. It'll sit there and look at you. But when you hook it up, you should start seeing a capture. I asked for 10,000 cycles. You should be seeing 10,000 or 10,001 cycles. So lab 1, I just dropped 2 weeks. Lab 1 starts tomorrow night, 4:30. 2300 ends at 4:30. So you probably won't be able to get in there early. If you've built a board, start using the board. If you haven't built a board, start using the microstick. Any questions at this point? More to follow on Wednesday.